title will be Closer to the Edge, Testing Compilers More Thoroughly by Being Less Conservative About Undefined Behavior. So let's welcome Karine. So can you share your screen?
Yeah, I'm trying. I'm trying to yeah. Can you see my screen now? Can you see it now?
I can hear you, but I can't see the screen. I can hear from you clearly, but I can't see the screen sharing.
You can't see the screen. Okay. Up here on top. Okay. I'm doing it. Okay. Now you're supposed to see my screen. And can you see it now?
Yeah. Awesome.
Yeah. Okay. Great. So we can start. Then you can see the slide. Yeah.
Yeah.
Yeah. Okay. So I'm Karine. I'm going to present the work I'm doing with Cristian, Cadar, and Alastair Donaldson on compiler testing and fuzzing. So fuzzing is an efficient and successful method for testing compilers in which we aim to expose miscompilations via differential testing. A test case is a program which we can compile, which we can compile with a compiler A, get a binary, run it, and get the result A. We can repeat this process with the compiler B. Run it, get a binary, run it, and get the result B. If result A and result B are not the same, then we found a miscompilation that can affect any program that we compile with this compiler. The main challenge when testing a compiler is generating a program, generating programs that are free from undefined behaviors. Undefined behaviors can be, for instance, dividing in zero or assigned integer overflow. Non-UBIFI programs have unpredictable program result that don't describe a problem that is a bug and cannot consider as a valid bug. One of the successful and common tools for compiler fuzzing is SysMit that found and reported many bugs in mature compilers. It has during and post-generation solution to assure it generates UBIFI programs. For arithmetic operators, to avoid undefined behavior, it uses safe math wrappers. It looks something like this. So we have unsafe check that says that if A and B on operator circles might or can trigger undefined behavior, then we return A. Otherwise, we return the result of A, circle B. If we look at the example on the right, then we have in the for loop plus and division. And if we want to use this test case to test the compiler, then we have, and we want to assure we are not triggering any undefined behavior, then we're going to replace it with the wrappers with safe add and safe div. For division, it looks something like this. So we have if B is equal to 0, then in order to avoid triggering undefined behavior because of division of 0, we return A. Otherwise, we return the result of A divided by B. During time, compilers became immune to these fuzzers. And in the next two slides, I'm going to present our observation and hypothesis that leads to new bug report. This is code fragment of a test case, of a real test case from SysMit, where you can see safe math wrappers also for multiplication, shift, modulo, besides add and division. There's one that mark in yellow. So there are quite a lot, and it's several lines from the test case. An interesting observation is that these checks appear several times in instructions, and we don't see any of these operators as is outside of the ternary operator. This can be a problem because some of the code optimizations in the compiler can be inapplicable if enclosed in these checks. We hypothesize that these wrappers limits the form of program we can generate because actually they are everywhere. If we look again at the example from before, we do need safe div because when we pass through 0, we will have a division in 0, but we don't need plus safe add because the plus is okay. We start from 5 and then we add 8, 7, and so on. So we never trigger an undefined behavior. And by using this idea, we're going to show how we find new bugs in GCC. And the idea is to be less conservative when generating UBIFI programs for testing compilers. So we have the generator, which is in our case SysMit. It creates a test case. Then we're going to use our dynamic analysis to identify and eliminate redundant checks and output a relaxed test case only when it's needed, going to include this test case. If we look at the example from before, so the original test case includes safe add and safe div, but the relaxed test case leave the plus operator as is. We did an evaluation with 100,000 test case. We found 2 new bugs in GCC 10, we reported them. It was with P2 normal in pointers in the tree optimization code. These were fixed promptly and can only be discovered by a tool sysmit edge. Since we wrote this paper, we managed to report several more bugs that confirmed and fixed. In addition, the line coverage was increased in 4,000 lines in compared to sysmit, which you can see on the graph on the left. So the green line is the coverage achieved by sysmit, and the light blue line is ours. In the future, we are going to use our tool to try to find more compiler bugs, not only in GCC, but also in LLVM and in Microsoft Visual Studio. We're going to, in the flow of our approach, we plan to extend the possible modification we allow in the relaxed test case, and also to explore the idea of relaxing the restriction during the generation of the test case itself, that is in the generator itself. The restrictions that are related to generating UB3 programs can be, for example, forcing initializations of a variable when declared, or controlling the index's value when accessing an array. Then, after this, we can use sanitizers and static analyzer to detect and discard those with undefined behaviors. If we have a test case without undefined behavior, we can just use it as a regular test case. That's all. I'll be happy to answer any questions.
Awesome, thanks. So any question? Any questions? So I can check the mobile app. There are currently no questions asked. Okay. Anyone has any question? So I have a quick question that I have seen that the GCC started to aggressively optimize the undefined behavior maybe since the version of 6 or 7. So, but I think I also encountered some optimizations that lead to unexpected behavior. And I personally is considering aggressively optimizing undefined behavior. It's not a very much good choice for the compiler designers because normally they, only in very minor cases, they can get some performance plus, but for many times they create programs that are difficult to debug. So what's your opinion about this? Should compilers do aggressive optimization on undefined behavior?
I'm not sure they're really, so yes, we found some bugs because there was an optimization that they thought the optimization was buggy, and then it kind of triggered an undefined behavior because it gets to the wrong place. But I think I believe it's fine. So if you know, you might, if you think of it, you might trigger undefined behaviors because you're not supposed to get to this area. So for instance, if you decide you take care of division of 0, you might, you know, in a way that it will not mess up the whole program, then you might add much more code that you don't need. So yes, you're not supposed, I don't think you're supposed to add more code of things that might happen. You know, some programs can be much more complicated when it's straight line.
Yeah, but if the compiler optimizes this undefined behavior, it will produce very weird code, like removing a print statement or something else. So in some cases, creating some trouble for debugging. And like the kernel now compiles with the fwrapv option, so all integer overflow wrap rounds. So yeah.
But you can debug without the optimization. Like you can use, if you put this as optimization at any level, then yes, it's bad. But you can say that if I'm on debug, I'm using a specific flag that is not going to use all these optimizations, and then look what's the problem. Maybe, I don't know, you see that you somehow thought you get to this if with this value, but actually you enter this block with different values. Then you can find it with the debugger, but you don't need to carry it all the way into your code. If it's like, I don't know, kind of production environment, yeah.
Yeah, thanks very much. I think any question? We have time for one more question. So please raise your hand if you have a question. So yes, nice, I think. So yes, I can conclude with this session. We have 4 wonderful talks about systems and compiler testing. And I think the session will end here. Thanks all the speakers and all your participations. Yes, thank you very much. So see you in the next session, maybe. Yeah. So thanks.
Yeah. Thank you.
Thank you all. So I think we are done with this session. Yeah.
Thanks, everyone. I'll end the session now.